For this group with elements 1, 3, 5, and 7, we are tasked for this video to identify its corresponding subgroups. Yes, this set G is already identified as a group under multiplication modulo 8. We actually had this Katie's table as well as our guide before. We have that one video. Please try to review that. And we'll also be using the same Cayley table here. Now, if we're talking about subgroup, they are actually subsets of the given group. So that would mean we'll be trying some different combinations, but we actually have a guide for this. And let me reintroduce the Lagrange theorem. Okay. The Lagrange theorem tells us that for any group and its cardinality or order is already identified as a positive integer. Of course, cardinality means positive. We have 4 elements there. Any subgroup H would have orders equivalent to the positive divisors of the order of your group G. Our group G, or the order of group G, is 4. So the positive divisors of 4 are 1, 2, and then 4. In this case, we are assured that we will no longer try to come up with any attempt to identify subgroup of order 3, because we are assured that our subgroups will have order 1, 2, and 4. And by the way, don't forget the caution I've made when we discuss the Lagrange theorem. It doesn't mean that if there is a possibility for a subgroup with order 2, we will really try to identify any, we will really look for possibility if we have met already some options that are not. We really take time and look for that subgroup of order 2, because it's not an assurance for the converse of the given statement, but we are guided that there is a possibility for any subgroup of order 2. Now, by the way, similarly, just another caution, it doesn't mean that we have identified already one subgroup of order 2, then we cannot have any other subgroups of order 2. Again, we are going to check that for this video. So for this time, we are now going to start with identifying the first subgroup. This corresponds to the subgroup of order 4. It's actually the group itself, set containing 1, 3, 5, and 7. The group itself is also a subgroup, since a subgroup is a subset, and we have considered before that any set is a subset to itself. It's actually considered as an improper subset. This time, the group is also considered as an improper subgroup of itself. So we are done with a subgroup of order 4. There are no other possibilities, because here we have 4 elements, and if we're talking about set, regardless of the arrangement, it's just the same. Next is to proceed with a subgroup of order 1. Always remember that if we're talking about the subgroup of order 1, it's the set containing the identity element of our given group. Now, the identity element here for this subgroup is also the same as mentioned as the identity element of the given group. So we have here our Cayley table, and the guide here is actually to identify specific rows and columns where when we operate the elements, they do not change their values. You can also try to check the video discussing the proof for this group to be a group, because we are also discussed there the existence of the identity element of the given group, which will also be the identity element to be placed for this subgroup of order 1. And if we're going to look at this, we know that when we have 1 star 1, the result is 1. 3 star 1 is a 3. 5 star 1 is 5. 7 star 1 is actually 7. So when we try to operate all these elements by 1, they do not change. Similarly, 1 star 1 is 1. 1 star 3 is 3, 1 star 5 is 5, and 1 star 7 is 7. See, when we operate again 1 to any of those elements the elements do not change their value. This means that our identity element here is just equal to 1. So our subgroup of order 1 is the singleton, or the unit set containing the identity element, which is equal to 1. So we are now sure with the first two subgroups, yes, subsets which are considered as a group. This time, let's look into the possibility of coming up with subgroup of order 2. Order 2 means we are to consider any pairs of elements. But before we list them or list the possible items to be verified, let's be guided that for a certain subgroup to be really a subgroup, it should have an axiom of groups. The first one is that the identity element should be existent in all subgroup. And since we are talking about subgroup of order 2, one of those elements should be 1, our identity element. So our possible subgroups here are 1 and 3, 1 and 5, 1 and 7. No need to write 1 and 1 because there's duplication. It's just the same as that. So we will not be introducing that as one of those pairs or possible subgroups of order 2. Since here we are assured that for the 3 of them, the identity element are already existing, the next part is for us to identify whether in that same pair there exist inverse elements for every element, not just for one, but it includes 3. Okay, so what are the inverse elements of 1 and 3, even 5 and 7 for the next item? Let's return to our KD table, and our KD table will actually tell us the inverses. To determine the inverses, simply look at the KD table and where can we locate our identity element of 1. Our identity element of 1 is here, 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 and here. Then you try to determine what are the elements that are operated that will result to that, and you would know the inverses of the other. When we have here 1 star 1, the result is 1. That would mean the inverse of 1 is just 1. Next, 3 star 3 is also equal to 1. So the inverse of 3 is, the inverse of 3 is also itself. 5 star 5 is the location for our 1 here. So we can say that the inverse of 5 is also 5. And finally, 7 star 7 will result to 1. So the inverse of 7 is 7. Surprisingly, we can see here that the inverse of the element is itself, unlike the previous example. That would mean it's easier for us to identify the possible inverses of the other. Looking at the first pair, the inverse of 1 is 1. Check. The inverse of 3 is 3. Check. So we do not drop that. But we cannot decide yet that it is already a subgroup, but we cannot drop that because it follows the existence of identity and their inverses. Similarly, inverse of 1 is 1, the inverse of 5 is 5, so its 5 is already there, so we keep that in the meantime. Next, for 1 and 7, the inverse of 1 is 1, the inverse of 7 is 7. So all of these 3 pairs are still possible subgroups. None of them were crashed out because they do contain identity element and the inverses of the other inside. Again, we cannot yet tell that they are actually subgroups because we still have the last one, the idea of closure property. Meaning, if we're going to operate all the elements here, the result will also be here. So we have 1 star 1, 3 star 3, 1 star 3, and 3 star 1. If the results would either be 1 and 3, we will accept this. Looking into our KD table, 1 star 1 is actually 1. 3 star 3 is also 1. It's right there. 1 star 3 is 3. 3 star 1 is 3. So the results are just 3 and 1. So again, this is 1, 1, 3, and 3. They are all elements of that. This time, we cannot really say that it's already accepted as a subgroup. So do we stop here? No. Even if we have identified already the existence of a subgroup with order 2, as mentioned earlier, we do not stop because we still have 2 pairs that are still possible, for they include identity element and the inverses of its every element. Okay, we need to examine all. It doesn't mean that according to the language theorem, we have identified already a subgroup of order 2, then we stop, because there is a possibility that those 2 would still be considered as subgroups. Looking into this, by closure property, 1 star 1, 1 star 5, 5 star 1, 5 star 5. So 1 star 1 is 1 based on this. And since 1 is an identity, so they return to 5. Okay. How about 5 star 5? It's also equal to 1. So we can see, sorry, if you were not able to follow, 1 star 1 is just a duplicate of that. So 1 star 5 and 5 star 1 is automatically 5 because 1 is the identity element, right? As mentioned earlier. So what we check is only the remaining item. 5 star 5 is actually 1. So all of these are elements of this. So this is also another subgroup of order 2. Yes, we can have more than one subgroup of any order as long as they actually satisfy the axioms for subgroup. How about 1 and 7? So 1 star 1, as mentioned, is still 1 based on this. 1 star 7 is 7 because 1 is identity. 7 star 1 is also 7 because 1 is identity. How about 7 star 7? We know that it's actually 1 because they are inverse of the other. So we can see that 1, 7, and 1 are also part here. So we actually have three subgroups of order 2. Unlike the previous video where we only have a subgroup of order 2. So all of them are accepted. Take note, we will no longer try any subset of order 3 because according to Lagrange theorem, it's no longer possible. Hence, the subgroup of your G, which is equal to the set containing 1, 3, 5, and 7 are the following. 1 is itself 1, 3, 5, 7. This is a subgroup of order 2. Next, the set containing the identity, that's a subgroup of order 1. And we have 1 and 3, 1 and 5, and 1 and 7, the subgroups of order 2. Yes, there are 5 subgroups for the given group identified in this video. So simply follow all of this to verify other examples. We will have one more example pertaining into the operation of multiplication modulo, but it's on a different modulo. It's also a group that we have identified in one of the videos. So the next part is to identify the subgroup of that given group. It will be for the next one. Thank you very much for watching.